So cholesterol itself is a key component of cell membranes, and it also provides an essential precursor for steroid hormone synthesis. So we're going to talk briefly about the synthesis of cholesterol, but most importantly, the regulation of its synthesis. So before we start there, what I want to draw your attention to is that all 27 carbons come from acetyl-CoA for cholesterol synthesis. And if we remember back from glycolysis, glucose is again oxidized to pyruvate in the mitochondria, which is converted to acetyl-CoA. Acetyl-CoA condenses with oxaloacetate to produce citrate, which we know from fatty acid synthesis can be shuttled out of the mitochondria into the cytosol, and the cytosol will be our location for cholesterol synthesis. Once in the cytosol, our citrate is cleaved by citrate lyase back into acetyl-CoA and oxaloacetate. This acetyl-CoA pool in the cytosol will serve for both fatty acid synthesis as well as for cholesterol synthesis. So the full pathway of cholesterol synthesis is illustrated here. So we start with our acetyl-CoA in the cytosol, and the initial condensation of acetyl-CoA is to mevalonate. This conversion here is our first stage of cholesterol synthesis and will be our focus, as this is our regulation of the pathway here. The subsequent steps in the pathway are largely unregulated, and mevalonate is used to synthesize our isoprenoid units. These 5-carbon chains are joined in a head-to-tail fashion to generate squalene, which is 30 carbons and undergoes a cyclization reaction after epoxidation. Our cyclized product, linosterol, undergoes several reactions to generate our final product, cholesterol. Again, we're going to focus on our first step here in this transition. So again, in this first stage of synthesis, we start with 2-acetyl-CoA and we finish with the product mevalonate. This is our committed and rate-limiting step in cholesterol formation. And in this reaction, we condense our 2 molecules of acetyl-CoA, forming aceto-acetyl-CoA. This in turn condenses with a 3rd molecule of acetyl-CoA. And this yields a 6-carbon intermediate, which is beta-methylglutaryl-CoA, or HMG-CoA. Our major point of regulation in this process is the enzyme HMG-CoA reductase. You can see here it's negatively regulated by bile acid as well as cholesterol, and also inhibited by its own product, mevalonate. It's also the target of therapeutics, as this is where our statins will also inhibit. So in addition to this inhibition of HMG-CoA reductase by allosteric inhibition, there are also several other means by which this enzyme is regulated. So the additional regulations are shown here, and we'll talk first about phosphorylation. So phosphorylation will inactivate our HMG-CoA reductase. Phosphorylation is stimulated here by high levels of glucagon. So in the fasted state, we're not synthesizing cholesterol. As we've seen previously, glucagon will enhance production of cyclic AMP, and this will inhibit a series of protein phosphatases, which allows for the phosphorylation and activation of the enzyme AMP-dependent kinase. This kinase will then phosphorylate and inactivate HMG-CoA reductase. We'll also note that HMG-CoA reductase is regulated at the level of gene transcription. High levels of intracellular cholesterol, either through cholesterol efflux or from synthesis, can inhibit the transcription of HMG-CoA reductase. And this is done by inhibiting the transcription factor, sterol response element binding protein. High levels of intracellular cholesterol can also target the enzyme HMG-CoA reductase for degradation. So again, the enzyme HMG-CoA reductase is regulated through allosteric inhibition, through phosphorylation, it's regulated by degradation, and it's regulated at the level of gene transcription. So let's finish with this quick question. Under fasted conditions, glucagon is now elevated, and which of the following enzymes will be phosphorylated and inactive? So we're in the fasted state here. So if we remember back to some of our regulatory enzymes in the fasted state, we'll know that all of these would be phosphorylated and active. So that may help us here. So first of all, HMG-CoA reductase. We've just looked at this, and we know that it will be inactive when phosphorylated. So this seems like a good choice. Hormone-sensitive lipase. Now this is a fasted state enzyme. Remember, it's responsible for lipolysis in the adipose, and it would be phosphorylated and active under these conditions. AMP-activated protein kinase. Again, under fasted state conditions, the kinase is phosphorylated to be active. And finally, glycogen phosphorylase. Again, this is a fasted state regulatory enzyme responsible for glycogenolysis in the fasted state, so it would also be phosphorylated and active. This leaves us with HMG-CoA reductase being the correct answer here. Under fasted state conditions, this enzyme would be phosphorylated and inactive.